Effect of deficit furrow irrigation methods on yield and water productivity of tomato, Solanum Lycopersicum L., at Bako Tibe district of Western Oromia, Ethiopia. Abstract: improving water use efficiency is one of the important strategies for addressing future water scarcity, which is driven particularly by increasing human population. Enhancing agricultural water productivity is a critical response as it is by far the main consumer of global fresh water. A field experiment was conducted at Bako Tibe district of Western Oromia during the off-rain season of 2017/18 and 2018/19 cropping calendar to investigate the effect of deficit irrigation under alternative furrow irrigation, AFI, conventional furrow irrigation, CFI, and fixed furrow irrigation, FFI, methods with 3 water application depth of 100% etc., 75% etc., and 50% etc. on yield and water productivity, WP, of tomato, Galelia variety, for better agricultural production and environmental sustainability. The experiment was carried out as a 2-factorial combination of 3 irrigation systems and 3 water application levels in randomized complete block design with 9 treatments and 3 replications. Irrigation depth was monitored using a Parshall flume of an opening diameter 3 inch with discharge of 4.239 L/s at a head of 9 cm. Results were compared in terms of yield and WP at p0.05. There were highly significant differences between the mean results of both irrigation systems and water application levels on yields and WP. The interactions effects between irrigation systems and water application depth were highly significant on WP, while the rest were non-significant for both yield and WP. The maximum yield and WP of 27.85 tons/ha and 13 kg/m3 were obtained under AFI at 100% etc., while the minimum of 22.01 tons/ha and 9.8 kg/m3 were obtained from FFI systems 100% etc., respectively. Thus, AFI with 100% etc. application depth is found the best irrigation system for tomato production and recommended to be used for the communities of the study area and similar agro-ecologies. Keywords: deficit irrigation, irrigation systems, tomato yield and water productivity. Introduction. Water is one of the largest renewable natural resources, but fresh water is expected to emerge as a key constraint to future agricultural growth. The changing situation comes partly from increasing demands such as population, industry, and domestic requirements, partly from consequence of climate change. IJERT, et al., 2018. The major concern on future planetary freshwater resources are the effects of climate change on changing sea temperature and levels, drought and flood events, as well as change in water quality, and general ecosystem vulnerabilities. Su et al. 2015. The unpredictability of climatic events is of key concern to farmers in all countries, particularly in Africa. According to IJERT, et al., 2010, estimate the irrigation potential of Ethiopia was 5.3 million hectares. In terms of utilization, only about 12%, 857,933 ha, has been irrigated by 2015, FDRE, 2016. So, it is prudent to make efficient use of water and bring more area under irrigation through available resources. This can be achieved by introducing advanced methods of irrigation and improved water management practices. IJERT, al., 2018. Deficit irrigation is one way of maximizing water use efficiency for higher yields per unit of irrigation water used in agriculture. Geertz and Reyes, 2009, Nagaz et al., 2012. In deficit irrigation application, the crop is exposed to a certain level of water stress either during a particular growth period or throughout the whole growing season, without significant reductions in yields. FAO, 2011. The expectation is that the yield reduction by introducing controlled water stress will be insignificant compared with the benefits gained through diverting the saved water to irrigated additional cropped area. Hihon et al., 2007, Ali et al. 2007. Tomato, Solanum Lycopersicum L., is one of the most important irrigated vegetable crops and is one of the most demanding in terms of water use. Pete, 2005. The application of various deficit irrigation strategies to this crop may significantly lead to save irrigation water. Costa et al., 2007. In the study area, over-application of irrigation water without determining the crop water requirement were identified as the major problem of a crop failure. Under such existing condition, practicing of deficit irrigation and water-saving methods of furrow irrigation systems could help to increase agricultural production by expanding irrigable land with the given limited amount of water. Therefore, the objectives of the study were to evaluate the effect of deficit irrigation under furrow irrigation methods on yield and water productivity of tomato for better agricultural production and environmental sustainability. Materials and methods. Study area description. The experiment was conducted at Bako Tibe district of Western Oromia. It is located at about 236 km away from Addis Ababa to Nakemt at east direction from Bako town at an altitude of 1,676 masel, Figure 1. The experimental site was characterized by clay loam soil type, dry and wet season with over 9 months wet period. The majority of the rainfall occurs from May to September. The area receives an annual rainfall ranges from 1000 mm to 100 mm and an average annual temperature of 190 C. /important files /Lemma_AGP_map.jpg. Map of study area. Experimental design and procedure. The experiment was implemented in 2 factorial combinations, namely, 3 irrigation systems and 3 irrigation water application levels, TABLE1. The treatments combinations were arranged as completely randomized blocks design with 3-time replications. The depth of water applied to the field was measured by Parshall flume of 3 inch throat diameter. The effective head of 9 cm was calibrated and hence the resulting discharge was 4.239 L/s. The plot size was 4 m x 10 m with 1 m and 2 m space between plots and blocks respectively. Each plot contained 4 ridges and 4 furrows. Each bed had 1 m width and 10 m length. The trapezoidal-shaped furrow was prepared with an average depth of 40 cm and width of 30 cm and 20 cm at the top and bottom, respectively. Where AFI 100% etc., FFI 100% etc. and CFI 100% etc. were alternative, fixed and conventional furrow irrigation with full irrigation respectively, AFI 85% etc., FFI 85% etc. and CFI 85% etc. were 85% of the full irrigation, 15% deficit, AFI 70% etc., FFI 70% etc. and CFI 70% etc. were 70% of full irrigation, 30% deficit, and AFI 50% etc., FFI 50% etc. and CFI 50% etc. were 50% of full irrigation, 50% deficit. Soil sample collection and analysis methods. Depending on the greatest root depth concentration, which is 30 cm for transplanted tomatoes, the disturbed and undisturbed composite soil sample before planting were collected at a depth of 0 to 20 and 20 to 40 cm. Different soil physical properties such as bulk density, texture, infiltration, field capacity, and permanent wilting point were done by core sampler method, pipette method, double ring infiltrometer, pressure plate apparatus by applying a suction of 1/3 and 15 billion Argentine pesos to a saturated soil sample, respectively. Determination of crop water and irrigation requirement. Crop water requirement of tomato for the growing season was determined from the reference evapotranspiration and crop coefficient using equation 1. Soil, Table 2, and meteorological datas, Table 3, were used to determine reference crop evapotranspiration, ETO. Farmers' experience was used to determine the numbers of days of each growing stages to estimate reliable KC for the respective growing stages. A higher value of application efficiency, 60%, was adopted, because water was applied more accurately and no runoff. Irrigation scheduling of the crop was computed using FAO Croquat program, Allen et al., 1998. Crop agronomy and management. Improved tomato Galelia variety having a total growing period of 90 days after transplanting was grown on nursery for 21 days and transplanted on experimental plots on January 15, 2018. The crop variety was selected for its good adaptability, disease-resistant and most usable in the study area. Tomato seedlings were transplanted to the experimental plots based on the recommended space of 60 cm between plants and 100 cm row spacing. Recommended fertilizer of 200 kg/ha DAP at the time of transplanting and 150 kg/ha urea twice, half at the time of transplanting while half at 21 days after transplanting were equally and uniformly applied to each treatments. The crop was cultivated and weeded 4 times during the growing season. It was transplanted on 4 ridges of each plot and for further analysis, the yield were harvested from the 2 central ridges to avoid border effects. Depth and discharge measurement. The total amount of water requirement for the crop was diverted to the furrow with calibrated Parshall flume having appropriate opening diameter of 3 inch, 3, with a length of 2 m and its appropriate head ranges from 3 to 33 cm. It was calculated as suggested by Michael, 2008. Results and discussions. Crop water requirements and irrigation scheduling of tomato. Crop water requirements were calculated by multiplying the reference evapotranspiration values with the tomato crop coefficient, Allen et al., 1998. The seasonal irrigation water requirement of tomato was found to be 2,992 cubic meters. This amount of water was needed for 100% etc. with CFI, full irrigation, level treatment, while 75% and 50% of 100% etc. with CFI were 2,244 and 1,496 cubic meters, respectively. The total irrigation water applied to AFI and FFI systems with 100%, 75%, and 50% were 1,496, 1,122 and 748 cubic meters accordingly. The depth of irrigation water required at each irrigation interval and number of irrigation events were described on Table 4. The result indicates that the maximum depth of water was applied during mid of March, which is the mid-development stage of tomato. Sahasrabudhe, 1996, suggested that this is the time when the crop needs high amount of water. Maximization of crop yield and quality can be achieved through meeting crop water requirement during this critical period, given all other factors are met. Probably the high tomato water requirement during this stage of development can be accounted for development of flowers and fruit, which is high energy demanding and peak physiological phase for the crop growth. Sahasrabudhe, 1996. By sufficiently supplying water to the plant, during such critical time and ensuring its uptake, it is possible to improve crop water productivity. Where CFI, AFI, and FFI are conventional furrow irrigation, alternative furrow irrigation and fixed furrow irrigation, respectively. Effect of irrigation systems and water application levels on tomato yield. The analysis of marketable tomato yield showed that both irrigation systems and water application levels were highly significant at P0.5 on yields, Table 5. But the interaction effect between irrigation systems and water application levels, irrigation systems and year, water application levels and year, water application levels and year and irrigation systems were not significant. According to Table 6, the yield obtained from the 3 irrigation systems and water application levels were significantly different from each other. The maximum marketable yield of 278.5 qt/ha and 299.8 qt/ha were obtained from alternative furrow irrigation, AFI, systems and 100% etc., while the minimum marketable yield of 220.1 qt/ha and 209.8 qt/ha were observed from fixed furrow irrigation, FFI, systems and 50% etc. water application levels, respectively. The yield obtained in AFI system was better than CFI system under 50% reductions in applied irrigation water. This is probably because of the better application efficiency and physiological response associated with AFI, Zhang et al., 2000, and less evapotranspiration associated with AFI, Stone et al., 1979. The significant yield difference among the water application levels were consistent with the report of continuous water stress during the period of fruit set and fruit development can result significantly reduced fresh fruit yield and blossom end rot, Sahasra Budhi, 1996. Effect of irrigation systems and water application levels on water productivity. As depicted from the analysis of variance, Table 5, irrigation systems and water application levels and their interaction were highly significant at p0.5 on water productivity. However, there were no significant differences between the interactions of irrigation systems and year, water application levels and year, water application levels, year, and irrigation systems. The water productivity of the three irrigation systems and water application levels were significantly different from each other. Table 7. The maximum and minimum of 13 kg/m3 and 9.8 kg/m3 water productivity were obtained from AFI and FFI, respectively. This is because of the higher rate of lateral flow towards the dry soil part in AFI system under low water application levels rather than downward flows. This is consistent with the significant improvements in water productivity that have been associated with AFI and FFI. Fayan and Zarihun 1999, Casa, 2001, Woldesanbut, 2005. The maximum and minimum water productivity of 13.7 kg/m3 and 9.9 kg/m3 were observed under low and high water application levels of 50% etc. and 100% etc., respectively. Both irrigation systems and water application levels were better in water productivity under low irrigation water application depth. This is because of the difference in percentage of water actually converted to evapotranspiration out of the total amount applied. Interaction effects between irrigation systems and water application levels were significantly different on water productivity, Table 5. According to Table 8, water productivity was highly influenced under FFI systems at 100% water application levels. This may be due to the application of irrigation water to the fixed furrow of the plot throughout the growing season of the crop. Partial budget analysis. From the economic analysis results, Table 9, AFI with 100% etc. is better in marginal rate of return and more advantageous to irrigators. Because, for 1 bear/ha on average invested cost the farmers may get 1 bear/ha plus an extra of 90.87 bear/ha net benefits. In addition to this, the net benefits of 22,940 bear/ha is obtained while changing from CFI system with 100% etc. to AFI system with 100% etc. under 50% reduction in volume of applied irrigation water. This means 2,992 cubic meters volume of water is needed to irrigate 1 hectare area in CFI system, which is enough to irrigate 2 hectare area of land in AFI system. So, when the area to be irrigated becomes double in AFI system using the saved volume of water, the yield and income obtained also becomes double. Where D, MRR, .MR, and .MC were dominance analysis, marginal rate of return, change in marginal revenue and change in marginal cost, respectively. Summary and conclusions. Tomato needs high amount of irrigation water during the flowering and fruit setting stage, and continuous stress significantly reduces fresh fruit yield, especially in FFI system as half of the roots stay dry throughout the growth period. The irrigation water used in AFI system is 50% of CFI system, but the tomato yield obtained was similar. Because in CFI system 4 furrows irrigated at the same time while in AFI and FFI only 2 furrows out of 4 furrows. This may improves working conditions as technology allows irrigator moving on the dry furrows. It is possible to double the irrigated command area by using the saved irrigation water. Over-application and high-frequency irrigation was a known constraint in the study area, and giving training and advisory service for communities on how to use crop water requirement-based irrigation system will be a better solution. Alternative furrow irrigation system at 100% etc. is the best technology among the tested technologies to be recommended for the communities of the study area, because of its high net benefits, water productivity and yield performance, in addition to time and irrigation water saving.